So we've got a parallelogram and it gives us the coordinates of point B, so that's at the point 5, 8. Doesn't give us any other coordinates, but it tells us the vector AB and the vector, it also gives us the vector AC, so it tells us what that vector there is. Okay, now first thing we've got to do in part A is find the coordinates of this point C up here. Now I think because we know the coordinates of B and we know the vector A to B, we should be able to use that information to find the point to find the point A, and when we've got the point A, we use the vector AC to then find what point C will be. So the vector AB is actually the same as the position vector of B minus the position vector of A. Okay, now of course we know what the position vector of B is because we're told the coordinates of B. The position vector of B is 5, 8, because remember the position vector is the vector that goes from the origin, I'll draw it in, it goes from the origin up to B. So that vector there is the vector OB, otherwise called the position vector of B. Now, and we're trying to find the coordinates of A, so what we're trying to find actually is the position vector of A, but we know what the vector AB is. It tells us it's 2, 7. So if we just rearrange this equation, we're going to get RA equals 5, 8 minus 2, 7. And that's 5 minus 2 is 3, 8 minus 7 is 1. So that tells us the position vector of A, which again I can show, it's that line there. Okay, that's the position vector of A. That's 3, 1, which means we can also write down the coordinates of A now, and A is the point 3, 1. Okay, and what we can do now is we can say, right, the vector AC, which we are told, but we also know that's the vector, position vector of C minus the position vector of A. Okay, now we're trying to find position vector of C, so RC is what we're trying to find, but we know position vector of A is 3, 1, and we know that AC is, it tells us 10, 11. Okay, so we can say that the position vector of C is going to be 10, 11 plus 3, 1, which is 13, 12. So that's the position vector of C, and it wants it as coordinates, so to write it as coordinates we just write it as a horizontal, horizontally like that, 13, 12. And there we have it. Now the next part, it gives us another point, the point E, and this point 63, 211. So that's going to be miles off the diagram. But what that tells us is if we think of what the vector AE will be. Now the vector AE will be position vector of E, which is 63, 211, minus the position vector of A, which we know is 3, 1. So that's going to be 60, 210. Okay. Now, if we now think about the vector AB, the vector AB, it tells us, is 2, 7. Okay, so if we find that the vector, so if I do a sketch, imagine this situation. So here's point A, here's point B, and here, say, is point E. Of course, I'm assuming that ABE is a straight line. But the way we can actually test that mathematically is if it's a straight line. So if straight line, what that means is that the vector AE must be some scalar multiple of the vector AB. But we know the vector AE is 60, 210, and move it up a bit. We know the vector AE is 60, 210, and the vector AB is 2, 7. And 2 goes into 60 30 times, but 7 goes into 210 also 30 times. They both go 30 times. So that tells us we can write vector AE as a scalar multiple of the vector AB. Therefore, ABE is a straight line. So as AE is a scalar multiple of AB, ABE is a straight line, and we've proved it. And the important point in the proof is this line here, where we show that the vector from A to E is just a constant scalar multiplied by the vector from A to B.